Hi, welcome to video 6.1b, more on slope fields. Okay, so be careful. On the AP, they're going to ask you to match the differential equation with its slope field. Similar to 57 through 60, so they give you 4 slope fields and they want you to decide which one of these is the slope, which is the slope field for which differential equation. Now you got to be careful because don't misinterpret and say, oh, I'm looking for the graph of y equals sine 2x, and that's not what you're looking for. You're looking for the graph of some function y whose derivative is the sine of 2x, okay? Over here, number 60, whose derivative is 1 over x. You are not looking for the graph of 1 over x, so you have to pay attention to that. All right. Now, for example, if, hold on. Hey, sorry about that. Okay, so if they give you dy dx equals sine x, and they give you this as a choice, this would be very tempting because you're looking at the graph of y equals sine x, but this is not y equals sine x, it's dy dx equals sine x. So one option is to actually solve the differential equation, send the dx to the other side, in other words, separate the variables, y is on one side, x is on the others, integrate both sides, the integral of 1 dy is y, the integral of sine x dx is negative cos x plus c. That, of course, you should know what the graph of y equals negative cosine x looks like, right? Because cosine x would start at the bottom, so you probably think of it as this middle one here, okay? And then plus c, so it would look like that. So you'd pick one that looks more like this. So do be careful that what you're looking at. So here's another just a very easy differential equation that we can solve. dy dx equals x. Separate the variables. Y is on one side, x is on the other. Integrate both sides. You'll get y equals x squared over 2 plus c. And that's a family of parabolas. Not very steep because of the 1/2. And of course the plus c just moves it up and down. Okay, so here's the matchy ones. So number 58, dy dx equals a half cosine x. Which of the following is a graph of that? Well, it is trig, so you would expect that it's when you integrate it, you'll get another trig function. So there's 2 ways you can do these. One of them is you can actually check the slopes at certain grid points. For example, at the point 0, 0, for this differential equation, the slope, dy dx, would be 1/2 the cosine of 0. Well, the cosine of 0 is 1, so at 0, 0, you should have a slope of a half. So that would eliminate option B because the slope at 0, 0 is 0. These are all horizontal lines. It would also eliminate A because the slopes are undefined because they're vertical little tangent slopes. So the only options then would be B or C, which at 0, 0 look pretty well the same. Okay. Then if you have two graphs that have the same, then pick another point. I'm going to pick pi over 2 comma 0. Which, it would be an actual kind of grid point here for a trig function. So if I plug in pi over 2 for my x, cosine of pi over 2 is 0, I should have 0. So at pi over 2, which is at 1.57, I should have 0. And, well, we've already eliminated both of these anyways. And now pi over 2, 1.57, which would be about here. I mean, I guess this one looks more like a horizontal tangent line. You might have to go further on that one. So the only slope field is answer C or D that satisfies these slopes, and you could try more. The other method is to actually solve the differential equation if possible. That's not always going to be possible, like with an x plus y or an x minus y won't be possible. But this one it is possible. So we send the dx to the other side, so all the x's are on the right, all the y's are on the left. Integrate each side, we get y equals 1/2 integral of cosine sine x plus c. So if you're looking at these graphs, the only one that could possibly be it is answer C. Okay, so I'm going to look at calculus in motion now, their slope fields, just so you can see how this looks. Okay, so these are random graphs. I don't know which graph I really want to use. Let's use this graph. Okay, so they're going to show a slope column at x. So at this point x, these would all the slopes would look like for this particular equation. Okay. And then they're going to show them to you as the x's go around. Whoops, you see that? Show the slope field. Okay. All right, just to get a visual, reset, go with the first one. And show the slope field again. Okay, not that anybody's going to ask you to do this, but it's nice to have a visual. Okay. Okay, so slope fields with the TI Inspire. Now, they're not going to allow you to use the TI Inspire on the AP for slope fields. That would just oversimplify it for people with a fancy calculator. And the only reason I'm showing you how to do this is if you want to try other problems on your own by hand, you can use your calculator to check them. So in number 56, I think this is not even in the right chapter, page 250, whoops, 256, number 56, page 2, yeah, that's way back. Okay, so I'm not going to bother going back there. It says, use a TI to graph the slope field for the differential equation. Use integration by hand and the given point, which is the initial condition, to find the particular solution of the differential equation. Graph the solution and the slope field in the same viewing window. So we're given y, dy dx equals 2 root x with an initial condition of 4, 12. So this is how you can do this on your calculator, okay? You go into your graph mode. You go into graph mode. You're going to go to differential equations. So let me show you that. So you're in graph mode. You select menu and you select option 3, but you'll notice diff EQ. So option 7 will give you diff EQ, okay? It's hard to notice, but right there, that's a prime. That's telling you y1 prime. In other words, dy dx equals, you're actually entering the differential equation. And of course, the x0, x10, x0, y10 is your initial condition if they gave you one, okay? All right. Now, you will use x for x. That's easy. But for y, you're going to have to use y1 unless you've gone to the next function, which is y2. Then you're going to enter the initial condition right under the equation. You might need to adjust your window values to see the initial condition point. And here's an example where I graphed dy dx equals 2x minus y, and this is the slope field for this differential equation. And this yellow graph right here is the specific solution, the particular solution that goes through that initial condition. So if you go to the 0.13, you're right there, and that's, if you follow the little lines, that's where you would be. Notice I had to enter the function not as 2x minus y, but as 2x minus y1. And then you just tab down and enter these values right here. Okay? In 6.1, which is where we are, numbers 61 through 64, it says sketch the slope field for the differential equation. Use the slope field to sketch the solution that passes through the given point. Discuss the graph of the solution as x goes to infinity and as x goes to negative infinity. Use a graphing utility to verify your results. Now, they're actually expecting you to sit here and make all these little teeny tiny segments all by yourself, like going to the 0.00 and the point, whatever. I mean, that would just take an eternity. I would, if you're going to try some of these, try the ones where the numbers aren't too big, like that's 4, -4, try and stick around the origin. And, you should be able to get some kind of a slope field, but if you want to check and see if you've got the right slope field, you can do it on your calculator, okay? All right, so the equation we were given is, for number 64, is y prime equals y plus xy. So we're going to have to call that y1 prime equals y1 plus x times, that's crucial, y1, and then you're going to, so there it is, y1 plus x times y1, and then the initial condition is 0, -4. There's your slope field, and there's your particular solution. Let me actually show you one in action. So let's say we had the differential equation x plus 2y. I'd have to enter that as y1. And let's say I had an initial condition of 0, 2. Okay, press enter. There's your slope field. And there's the point 0.02 right there. You can see that initial point right there, and you can see that they've drawn the curve that goes through that slope field. Okay. So pretty easy to do. And that's the end of video 6.1b.